So I'm just going to finish off most of this talk. So we've been talking about transmission systems, standalone supplies. There are various systems we can use for a standalone power supply. So one to look at is AC-based systems, so similar to what we have in the grid, but you obviously need to be generating some form of AC output. Most rotating generators will generate AC, so that wind turbine will be generating AC directly. Typically AC-based standalone power supply systems are used for diesel generators and for micro-hydro systems. So this here is a micro-hydro, again installed in the Philippines. This is a 22 kilowatt micro-hydro system, cross-flow turbine. So micro-hydro is pretty predictable and controllable, so you know you've got a certain amount of water, you can probably adjust the valve to change the amount of water flow. And so it's pretty easy to interface it to a rotating generator, so as the water spins around, it spins something. And you can control the flow to give you a kind of constant output frequency within reason. We'll come on to what I'm talking about. I've said here synchronous machines are typically used. So this is a synchronous machine. I'll talk about that a bit later. Generally, for a system, an AC-based system with micro-hydro, you don't need to have any storage. What you're doing is you run the system at a certain value, and you design the whole system for the maximum load that people would require. And as long as you've got enough water to supply that, then you're okay, you can do it. But we need to ensure that the voltage and the frequency are kept within certain limits to ensure that our power quality is good enough. So the first way you could do that is a human operator. So it's a guy that stands there and he controls the valve, and if people turn on all their lights, then he opens the valve a bit more. He's looking at the voltage and the frequency. And that is actually how quite a lot of them are run. So when they're run, when people need them, there's a guy that just sits there. The issue with it is that it requires someone just sat there watching these dials, and people aren't generally, it's quite difficult for a person to stay there. So there were definitely issues where, one that I heard about, I went to see, was the guy had set it, so everyone had their lights on. The guy had set it so it was okay, he'd then gone off to do something else. And someone had plugged into a rice cooker and turned it on, and it caused instability. The voltage had collapsed, and then everything turned off, and then the micro-hydro system span out of control, and the voltage over-voltaged, and it blew up everything. So it requires a human operator who's there and who's on it, and it's very difficult to do that. You don't really want someone who's employed full-time to look at a valve and move it. So you could also have a mechanical flow control, so you could control the flow through the system to follow the load. Problems with this, generally why it's not done, it's relatively slow to respond. So if you turn on a 2 kilowatt heater, it might not work quick enough. Also it needs quite a lot of maintenance. You've got a flow control valve, which is just it's quite a heavy bit of kit, especially if you've got 20 kilowatts of water pushing through it. You have to control that. It's just difficult to do. So the last thing we can do is electronic load control. So what we can do is we set the flow rate, and the electronic load controller will dump any excess power. So it's fast, works pretty quickly, but it's relatively complex and requires power electronics. So just to block diagram of that, you've got your generator, it's shoving out a certain amount of power. If your load, say it's putting out 6 kilowatts, your load is 5 kilowatts, you have to dump 1 kilowatt. And in order to follow it, you have a control system which looks at the voltage and the frequency and controls the dump load. Generally dumped as heat. It's quite difficult to use that heat that usefully. I've seen it where they've dried fish on it. But apart from that, generally it's wasted, or hot water sometimes. So this is a system that's me, with Carlo. We looked at, we installed a kind of experimental load controller. So it's not very good photos here. This is the intake, this is the generator. It had 2 outlets. So this is a band which went to a rice mill, which is here. Or you could run it to electrical generator. Synchronous machine. There was a dump load outside which had water running through it, so it was generating hot water but water was cooling it. So that's one. There's another one here. This was in a different area. It's a three-phase bigger system, 20 odd kilowatts. That's the same photo we saw before. Three-phase system. There were 3 big dump loads dumping up to 20 kilowatts. I don't know if anyone's kind of, you know, a 2 kilowatt bar heater. It's quite hot. 20 kilowatts when it's running. It's a lot of heat. Not really what you need in the Philippines, but. So that was the control system. This was a electronic load controller bought from Indonesia, and it went to supply a rice and corn mill. They had issues with it. I'll show you some photos of the issues with it. But that first system we saw, what had happened here was this is where the guy had not been monitoring the flow. That's why we'd installed an experimental electronic load controller. If it fails, it can cause serious problems. In this particular situation, there was no fusing, no protection of any of the loads. So when it overvoltaged, it just overvoltaged, and this is a lighting ballast which has caught fire or got very hot, and every single light in the community had blown up at that point, which is a bit annoying, costs people quite a lot of money. So yeah, that's one of the problems. If it fails, you can get overvoltage, and that can cause serious problems. Also, they're not produced locally, generally not produced locally. There's not huge demand for it. So we can also look at DC-based systems. So photovoltaic panels generate DC, direct current out of these. Wind turbines actually generate wild AC, which we rectify into DC generally. Also small hydro systems, you can also use a DC system, you just rectify it into DC. Generally talking about relatively low voltage, 12 volts, 24 volts, 48 volts. I have worked on systems with 120 volt DC systems. You can get quite large battery banks. Generally we keep power ratings under 2 kilowatts within reason. This is about the maximum amount of energy input you're going to be putting out. Otherwise you'll have to go to higher voltages, big batteries. It all becomes a bit complicated. I was working with a 1 kilowatt wind turbine and they'd designed it as a 12 volt system. 1 kilowatt at 12 volts is 100 amps. That means that everything had to be rated for 100 amps. We needed a minimum of 50 millimeters squared of cable. So that's a 35 mil squared cable. So you needed big cables and long runs, and it was just, you need big fuses, everything's just got to be big. So I would prefer to go higher voltage, smaller cables, everything much easier. Typical system, generally we've got some form of energy storage, in this case the battery. You've got some wind turbine or solar power, you've got some kind of control system, some storage, and you sometimes have an inverter, which I'll talk about. It converts DC into AC. So I talked about rectification. Basically what we're saying is that as the magnetic field passes a coil, so in this case here, we've got magnets spinning round, or hitting into a bike, as the case may be, and they cause a varying sinusoidal magnetic field, which induces, which causes a current to flow in the windings, which induces a voltage. So the output from each coil has an AC output, but the frequency we don't know, because the frequency can vary, because it depends on how fast it's spinning around. So what we use is a bridge rectifier, diode rectifier. It's 4 diodes, or sometimes more if it's a 3-phase. I forgot to pick up. Where is it?
I think it's in that trolley.
It's in the trolley, isn't it? So this is a relatively big, high 75 amp bridge rectifier, and you basically bolt on the AC inputs into here, and you get DC on the output. You have a little bit of energy, a little bit of loss. This will get hot, so you do have to design that correctly. This is a 75 amp one, so the other issue with the 1 kilowatt 12 volt wind turbine was that we needed 100 amp or more rectifier, which is very difficult, very expensive. Yeah, sure.
With that AC power, is there any times when it's preferable to use a different waveform, like a different power?